As you see, my talk deals with transport properties of graphene. The aim of our study was to reveal how does configuration of different defects in graphene, of point defects and of line defects, affect the conductivity, increase the conductivity or maybe decrease the conductivity. Specifically, we consider how does correlation of impurities and line defects and even how ordering change the transport properties of graphene, change the diffusivity and hence the conductivity. To save the time, I will skip some pictures, especially because some information is very known for you. For example, about carbon allotropes and about graphene potentials. And I also will skip some mathematics because this work is theoretical, and our purpose was to calculate conductivity of graphene. To do it, we construct codes using C++. I want to say that we didn't use any packets like Quantum Express or VN or Siesta or some others, because these packets cannot work with very large systems. And so to reach our purpose, to calculate conductivity, we have to pass through some steps. First of all, we have to calculate density of states and time-dependent diffusion coefficient. To calculate density of states, we have to make some mathematical transformations using continued fraction technique and three-dimensionalization procedure for the Hamiltonian matrix, and some recursive calculation for Green's function. And to calculate diffusion coefficient for electrons, we solve quantum mechanical equation, Schrödinger equation, and we observe how propagate a wave packet over the graphene lattice. So we have a wave packet at the initial state, and then after some time this packet propagate, and for example we can see the position of the packet after 50 femtoseconds. As I have said, this wave packet is governed, is controlled by the Schrödinger equation. We use very efficient method to solve this equation. We use so-called Chebyshev method, where we expand time evolution operator into Chebyshev polynomials. And here you can see how wave packet propagate with different initial wave packet size. And some movies. You can see video the propagation of a wave packet with time. This is perspective view, and then will be top view. I will skip this picture, or some mathematics, and as well as this one. This slide shows us how we construct Hamiltonian, and we model defects in graphene. How we do it? There are different kinds of defects in graphene. First of all, we use Type-Winton model, which it is very commonly used model in the literature, and we try to model different kinds of defect, so-called short-range defects and long-range defects. Short-range potential represent defects with which are neutral adatoms. And there are strong and weak scattering regime. If we want to model charged screening impurities, we use commonly used in the literature in articles long-range Gaussian scattering potential. And also we model line defects in graphene. To do it, we use a self-consistent approximation from Thomas Fermi, and we use effective potential. We consider symmetric and asymmetric potential. When I say symmetric, it means that potential may be positive and negative. When I say asymmetric potential, that is potential may be either negative or either positive. And sometimes to simplify calculation, we can feed Thomas Fermi potential by a special so-called Lorentzian function, or Cauchy function, and you can see that this function feed very good this effective potential, where fitting parameters can be calculated, for example, from a least square method. The central quantity of this method is mean quadratic spreading of the wave packet. You see formula for this value. Also we use diffusivity or diffusion coefficient for electrons, and after some mathematics using the Kubo-Greenwood formula, we obtain the same as Einstein relation. And then we works in a diffusive regime where, for example, Ohm's Ohm law works, and in generally evolution of the diffusion coefficient of electrons pass through some regimes. When graphene is pure, is clean, there is a ballistic regime where diffusivity is linear dependent from time. When then diffusion coefficient reach its saturation, and then due to some quantum effects, localization occurs. And this equation, Boltzmann equation, of course, if we want to compare our numerical results with analytical results, we can use this approach. But I want to stress that our results are numerical. So we model different configurations of point defects. We consider them as random, as correlated, and as ordered. If we have the later case, when they are ordered, we consider two superstructures with two different stoichiometries. This is figure for short range impurities with two kinds of potential, symmetric and asymmetric. And if we model, for example, screen charge impurities, we use long range potential. And this is also a picture for random and ordered defects. Now we go to the results. First of all, we calculated density of states for these different configurations of point short range defects for weak defects and for strong defects, that is for weak scattering and for strong scattering. And you can see that density of states remains unchanged for short range and long range random and correlated impurities, but those can be essentially affected for ordered and especially for strong scatterers. You can see from these figures that some discrete energy levels appear, and they then can broaden as impurity concentration increase. But this situation is absent if we consider long range potential, because those practically coincide for both kinds, for both configuration of defects, for different set of parameters. This is results for diffusivity and for conductivity for short range weak and strong impurities. These results show us that conductivity is not affected, is the same for random and correlated impurities if potential is symmetric, But if potential is asymmetric, we obtain some slight increase in up to 30% of conductivity for electrons or for holes. But for strong impurities, conductivity practically is the same for different configuration of impurities, for ordered, for correlated, or for random. But situation is another if we have superstructures, if short-range impurities form some structure and if they are ordered. From this picture you see, from these figures you see that red curves are essentially higher than blue curves. This curve corresponds to the ordered location, ordered position of impurities, and right figures show us that increase in conductivity can reach up to 7 or 8 times. And this increase is stronger, is greater if the impurity concentration is higher. And the next slide is analogous curves, analogous figures, but for strong impurities. In this situation, conductivity increasing is stronger, is higher, because potential of strong impurities is higher. And but once again, in case of long range, for example, Gaussian impurities, we didn't obtain any increasing or decreasing of conductivity. Conductivity is the same for different configuration of this kind of impurities. Now we go to the line defects. To model line defects in graphene, we have to introduce so-called correlation angle. This is the maximal possible angle between any two lines in the lattice. We did it because we try to consider lines with different preferred direction. For example, if this correlation angle is 0, that it means that lines are parallel to each other, and as in this case, and if this correlation angle is equal to 90 degrees, it means that this angle can be randomly distributed. After diffusivity curves have been calculated, we see that conductivity along the line exceeds greatly conductivity in transverse direction. It's due to strong and weak scattering in these two directions. So we obtain anisotropy of the conductivity. And we see that these two ratios represent how conductivity increase or decrease, and conductivity increasing is stronger than conductivity decreasing. And that is why, even if these lines are parallel to each other, but are parallel to some preferred direction in each realization, conductivity for this case, for correlated lines, is higher than conductivity for lines which are distributed randomly. Moreover, we proceed for different number of lines. Here I write atomic steps. It means that we considered epitaxial graphene, where there are, due to morphology of substrate, there are some terraces and steps, and these steps, they act as a line defects. And we calculated how does conductivity increase with different content, with different number of lines in the lattice, with 10, 50, or maybe even with 100 line defects. And the last, before one slide, in fact, any graphene sample contains not only point defects and only line defects. We have to expect that there are simultaneously both kinds of these defects in graphene sample. So we also considered this situation, and from these figures you can see that, for example, if scattering potential is strong, conductivity are affected, but slight affected, because potential of point defect is strong enough. Of line defects, potential is weak. But nevertheless, for example, for a weak scattering regime for point defects, we see that conductivity behavior can be affected. And for example, it can be changed from a constant to some sublinear dependence. And maybe one of the most interesting effects for both kinds of defects is that in the presence of these two types of defects, we can the electron hole asymmetry, which was revealed when we considered these defects separately, this asymmetry can be suppressed. You can see it from this green curve. I will not read this conclusion. I only say that, to summarize, to conclude that if defects are described by long-range potential, correlation or ordering effect are absent. But if defects are short-range, we can see that correlation and especially ordering can increase the conductivity up to several times. And if we consider both kinds of defects, the conductivity can be not only affected change in the behavior, its behavior, but also due to correlation of point and line defects, conductivity can be increased, can be enhanced up to 100 times. I think maybe it will be the main question how we can put these point defects or line defects with some correlation, with a special correlation, or maybe even how we can create ordered structure. But this question, or rather for experimental physicists, and it is like a prediction, a forecast. And but if we can, if these results show that we can, this correlation and ordering can serve as additional tool to control the conductivity in graphene samples. Thank you.
Questions?
What about scattering on phonon? What contribution of phonon?
I don't know. I don't know, because in this model, I can only say that. In fact, scattering on phonon can be introduced by a special parameter, so-called scattering time. Its value is about. It's very small, and this scattering time can be introduced. But it is known that for graphene, scattering on phonons, that is temperature.
But sorry, is it your results are zero temperature?
Ah, yes.
So no phonons?
Yes, of course, of course. This cuboformalism works for zero temperature. Of course.
Next question. Thanks for interest.
So I think before the coffee break we have.
Coffee break.
How long was it?
15. 10 minutes.
Okay.
15 minutes.
Okay. We make a short coffee break, like 15 minutes, and afterwards we start next what time is that? And you will have yeah, the time. So 11, we should start at 11:30.
Aeroport? Okay?
Okay. I wish you good flight. Goodbye. We'll be in connection. Okay, goodbye.
Проверяли вначале решили, что какие-то духи Вангеев
I think it will be very interesting if experiments purities, basically